Welcome to the first of our science breakfasts for the year, and it's a beautiful morning in Sydney. I'd like to begin by paying my respects to the Gadigal people of the Eora Nation, the traditional custodians of the lands on which we are gathered this morning. Unusually, we actually have a welcome video from the Premier this morning, who has taken an interest in science. Here we go.
G'day everyone, New South Wales Premier Chris Minns here. I want to thank Professor Trevor McDougall for sharing his expertise today. In 2023, he was named New South Wales Scientist of the Year, and today he'll explore the complex relationship between our oceans and climate change. Climate change is a critical issue. As an island nation, we are all deeply invested in his work. Last year, the New South Wales government enshrined our net zero emissions targets into law. And we've made the largest ever renewables investment in the history of New South Wales. Now, we know we've got a lot more to do, but we're fortunate to have researchers like Professor McDougall to draw on. I hope you enjoy the seminar.
So it's great to have the first seminar. I have to say, I think we had 400 registrars for this talk, which is fantastic. And as people who've been to many of these over the years, for the last 15 years, I think these seminars have been running. This is a great, fantastic turnout. So today we are very privileged to hear from Professor Trevor McDougall. Trevor received his latest accolade at the Premier's Prizes for Science and Engineering held at Government House on 15th November last year. And as is tradition, he is the first speaker for this seminar series this year. Trevor is globally recognised as a leading expert in the field of physical oceanography and is the world's foremost authority on ocean thermodynamics. He has been recognised for his contribution to our understanding of the fundamental physics of the ocean, including how it moves and how it mixes. Trevor's contributions to the field of oceanography include leading an international group of researchers in redefining the 30-year-old definition of seawater thermodynamics and improving the accuracy of the treatment of ocean heat content by a factor of 100. As you would expect from such a distinguished career, Trevor's lists and awards and accolades is very, very long. I might pick out one or two, though, just to give you a feeling for where we are. Of course, the most important one, the 2023 New South Wales Scientist of the Year, awarded last year. But he also won the 2022 Prime Minister's Prize for Science. He is a Companion of the Order of Australia. He was a Laureate Professorial Fellow from the Australian Research Council. He is a Fellow of the Royal Society of New South Wales, a Fellow of the Australian Academy of Science, and a Fellow of the Royal Society of London. And that's just the beginning of the very long list. Welcome, Trevor.
Thank you, Hugh, for that rather flowery introduction. Do we have the slides up?
Yes.
Okay, so I'll put my glasses on. My first slide, I want to start with the actual record of the temperature of the surface of the planet in the last 170 years. And you see a lot of different coloured lines here, and the so I'll stay here. But maybe you can see the pointer here, right? So this, the different colours. The yellow is a figure from the UK. And so each of these groups have got the raw data on the planet's surface of the Earth, the ocean, ocean, land and ice, and figure out what the data is for each month of the year. And NOAA is an American, like CSIRO. NASA is American, we know what NASA is, and then Japan, and then European. But the interesting one is this Berkeley Earth, because the Heartland Foundation from America funded this professor of physics at Berkeley to redo the figures, because they were skeptical of whether the Earth was warming or not. And lo and behold, of course, when he looks at the data, there's only one answer, and it's all the same. So the planet's been warming, These little wiggles here are mostly El Nino and La Nina. The reason why it was going up a little bit here around the Second World War and then leveled off was all the aerosols from that rush into industrialization. So we do understand roughly what causes this, this graph. Another way of looking at it is this figure here with the oldest data in the top left, moving along the months to the right, the years to the right, and then down as though you'd been reading a book, with 2023 in the bottom one, partially completed in this data. And red means warm and blue means cold, so it's kind of obvious what that's about. This one here I like. It'll start in a minute. It starts in 1850 or so, and each month since then is plotted with a dot point and joined by lines. And you see there's just this trend to get warmer and warmer each month of the year. And the 1.5 and 2.0 degrees are the guardrails that the Paris conference sent us and recommended that we try and stay below 1.5 degrees warming at the surface of the planet, and said that if we go above 2, that we have an amazing number of negative outcomes. So these are different ways of looking at the same surface data, and here's another way. This way plots the months of the year on the horizontal axis, and each line is a year. You can't see them, I haven't labelled them, except for one year, and that's 2023. And that year it was warmer than any other year in the record by the amount shown in pink. So roughly, let's say a quarter of a degree or something. And we still don't understand why that is, by the way, and this is another way of looking at it, but this is actually the global sea surface temperature, so just the 70% of the Earth's surface that is ocean. This is the warming of that, and you see that roughly, again, it's about a quarter degree anomalous. So in those months between May and right up to the present day, actually, in 2024, it's never been warmer on this planet. This now is the similar data, but it's only the sea surface temperature in the North Atlantic. And you see the actual anomalous temperature here, the red is once again the extra temperature above any other year in the record. And you see here it's roughly 1 degree Celsius. So if something has been going on in the North Atlantic, which is very anomalous this past year, and we don't understand what it is, my bet is that for some reason the winds have been less in the North Atlantic, which means that as the planet warms, as the Atlantic warms, it wasn't mixed down as far as it would normally be mixed. And so it's been lying there as more undiluted as a warm, thin layer, perhaps only 50 metres thick. All right, another anomalous thing happened last year, and that was the very first time the aerial extent of sea ice in the Antarctic started to decrease in a rather dramatic fashion. You've heard lots of stories about that, I think. This was happening in the Northern Hemisphere, in the Arctic, but was losing sea ice, that's the floating ice. But this has now started to happen in the Antarctic. So that's all about the surface of the planet and warming and melting. But where does the extra heat go? So we have this greenhouse blanket around the planet, and there's extra transport of heat coming in. Where does it end up? Where would you find it? Where would you look to see it? And this is the answer to that question. In the colour here of purple at the bottom, that very small amount, that's the amount of heat it has taken to heat up the atmosphere. Very small. And the grey, that's the amount of heat's been required in the last umpteen years here to melt the ice that's melted. And a bit more heat has been used up to actually heat up the first few metres of the land. But all the blue here is where the heat is mostly. 92% of the extra heat that the planet has received from global warming is in the ocean. So it's the ocean, it's to the ocean you go to see how much global warming has happened. And the different colours here, how far, how deep in the ocean those warmth, those extra heat appears. Another aspect of the data which stands out is sea level rise. So globally, the ocean rises because of two real effects. Firstly, it's warmed up, so it expands because it's warmer. That's been the dominant effect this past century, and now an increasing effect. Probably half the signal now is melting of ice, and both those things are increasing. And you see here the record in the dark red line with the uncertainty in the pink. And it's been accelerating. So just in the 30 years of this record, the actual rate of sea level rise globally has doubled from 2.5 millimetres a year to 5 millimetres per year. And we can measure this very accurately by this little device that's shown here in this schematic, by satellite altimetry. It's amazing. These altimeters, 3 of them, circle the planet, and they can measure the height of the sea surface to within a few millimetres everywhere, even though there's waves and things going on. So that's the data on the surface of the Earth. And this is what's causing it. It's our use of fossil fuels. So the black line here until present day is our use as a species of fossil fuels. And if we kept going at this rate, we'd be going up here on the pre-Paris line. Current policy, if you look at all the governments of the world, their policies amount to this blue line here. And if my finger works correctly, I can show you this one, which is the current pledges as well. And this is a trajectory that we would need to be on if we were going to achieve 1.5 degrees warming and no more. Well, you can see that we're actually marched on a couple of years since this graph, and every year that we delay really serious action, every year the yellow graph, which is needed to control the temperature to a certain guardrail, becomes steeper. In other words, the actual temperature, oh my goodness, the actual temperature that we reach is actually proportional to the area under this curve, the curve of our emissions as a function of time. So we can either reduce our emissions and then we can emit for a bit longer to achieve a certain temperature, or we can keep on going on the pre-Paris policy line and then dramatically stop, physically, politically impossible, but that would have the same area under the curve, and it's that area which is important. And so if you look at this and factor in what you know about democracies and other countries in the world, it's very hard to see that we'd come anywhere close to this 1.5 degree line. And, you know, if I was a betting man, I'd say we're going to reach 3 degrees by the end of the century. So the news is not good. We've delayed for 30 years. We've had fossil fuel companies telling us this is not a problem, just like the tobacco industry did for 30 years, denying the science of Sir Richard Poll in the UK. Doll, I should say. And so this is our challenge, to look at this curve and say, how as a species are we going to address this problem? Because we already know we're getting many more floods. We have a rising sea level, which will soon, by the end of the century, will be 1 metre higher than it was at the beginning of the century. And there's 50 million people in one country called Bangladesh that live in that 1 metre range. And so you think we have had problems with boat people in the past. You've seen nothing until when sea level rises. All right, so I'm going to talk a bit more about science now. This is a schematic of what the North American country looked like 18,000 years ago, just at the end of the last ice age. And you see there was like 2 kilometres of ice over Canada, and even 1 kilometre of ice over where Trump Tower stands today. So there's nothing going on there except a very cold picnic. So what caused this? Well, a scientist named Milankovitch came up with the theory for this in the 1940s. And it's to do with the fact that the Earth and the Sun don't have, they have a relationship which varies with time. The Sun, the Earth moves around the Sun in a way which is not only circular, but varies from circular to elliptical in different ways. And also the actual angle of the Earth in relation to the Sun, the plane of the Sun, wobbles with time as well. And these upper 2 graphs indicate the magnitude, or at least mostly the frequency, of these 2 different oscillations. And they beat together to give the third figure here, which you can see has a dominant period of 0.1 million years, in other words, 100,000 years, which is the forcing timescale of ice ages. And so what that does is that causes a slight change in the amount of heat received by the northern hemisphere compared to the southern hemisphere. And the northern hemisphere is where the continents are, and the southern hemisphere is where the ocean is. And this slight change in the amount of heat then causes the carbon dioxide to come out of or into the ocean, because when the ocean's cold, or when a fluid is cold, it will absorb more gases. And so when the temperature on this red plot is cold, the concentration of CO2 in the ocean is larger, and the concentration of CO2 in the atmosphere is less. And so we understand what causes the ice ages. It's this slow beat of the Milankovitch cycle here. We also understand that ice ages are caused by the, first of all, temperature, and the CO2 follows by about almost 1,000 years later. And you can see there the sea level goes up and down by 100 metres. And this is in more detail. The top figure is the carbon dioxide concentration. You can see that over the last almost million years, we've had like 10 ice ages. And the variation of carbon dioxide is roughly 100 parts per million in those cycles. And you and I, and our parents and grandparents, have caused the carbon dioxide to increase from its highest level at the end of the ice age, at the end of this warm period here. We've actually caused an increase of 140 already. So a system which produces that ice over Trump Tower, caused by 100 parts per million cycle, and we've kicked it up by 140 above the maximum. So we've given the planet a kick, as in this last figure here. This is our modern kick we're giving the planet. First of all, it's a very high kick. The axis is high, and also it's a very sudden kick. It's happening in the blink of an eye in terms of how fast these increases of carbon dioxide happened at the end of an ice age. And here's, in more detail, the last 20,000 years. You can see we put this in perspective. Civilization was around here. Human beings, even Homo sapiens, have been around for 350,000 years. So there's, that goes much further to the left here. Mungo Man was living 42,000 years ago, not 22. So, but Christianity was invented here. This is quite a long period, if you like. If you think 2,000 years is long, or it's quite a short period if you're a geologist. And what we're doing is all in this red stuff here. We're giving it a big kick. All right, so the planet receives heat from the sun. It receives it mostly in the equatorial region. And so in the equatorial region, this is the amount of sunlight coming in. I wish I could point without doing that. And if it weren't for the fluid parts of the planet, the atmosphere and the ocean, then the equator would just keep on warming up to be incredibly hot, and the poles would be much colder than they are today. So the fluid parts, namely the atmosphere and the ocean, their overall role is to redistribute the heat from the equator towards the poles, and that's what it does. It's the atmosphere does the lion's share of it, and the ocean does its bit in green. And the ocean does that by two overall mechanisms. First of all, the horizontal circulation, and you can see the Gulf Stream here, putting warm water around to Europe, etc. And the East Australian Current coming down here, it should go north of New Zealand. This has been done by an artist, not an oceanographer. And the other way is a vertical circulation. It's called the thermohaline circulation for heat and salt. But the point of this is you have the red transports like in the previous figure, but once the water gets to the extreme northern parts or extreme southern parts, some of it can be made sufficiently dense to sink to the bottom. And that's what I depict here. This is the Antarctic water coming down, hitting the very bottom of the ocean at 5,000 metres, and similar things, well, I'll leave it. And if you pick apart the ocean into three ocean basins linked by the Southern Ocean and the continents, Australia occupies this vague space here. So this is an ocean-centric schematic. Then you see dense water falling down here from Antarctica and then coming up. So how does it come up? Well, that's where my work comes in, because to come up, it has to mix. It has to get less dense in order to be able to come up. So that's the vertical circulation. Another important physical process, particularly for sea level rise, is the melting of ice sheets, not sea ice, but ice sheets. So ice sheets are these things that are a few hundred metres at the ocean front and maybe up to 3,000 metres deep back here, and they sit anchored to the continent here. And then water comes in from the ocean and melts like this. This is the main mechanism for the 100-metre variation in sea level between ice ages and the warm period in between ice ages. Sea level is going up and down by 100 metres over 100,000 years, caused by the melting. This is the melting part of the process. Well, guess what? Today we have warmer oceans, and therefore we have more melting. And the really dangerous thing is if it melts enough such that this anchor point is no longer anchored to the continent and moves away. Not only does that happen up here under these ice sheets, which can be 300 kilometres in north-south extent, floating if you like, but anchored to this continent. But you can see a schematic of the sea ice that's floating and decreasing in extent, and also the changes in the bottom of the ocean. The ocean's getting less oxygenated, less oxygen in the ocean, more acidic. And I spoke about the melting under these ice sheets. Well, guess what? We've got satellites there that measure this from measuring the gravity of what's beneath the satellite, and they show that indeed Antarctica is losing massive ice like this, split between the west and the peninsula and the east Antarctica. And in the northern hemisphere, we're talking sea ice now, a very dramatic declines in 40 years of a factor of 4 or so in the volume of ice in the summer. So the aerial extent is less and the thickness is less. So I want to quickly talk about one technology that we use, which is a really cool technology. It's called Argo floats. That's the size of it. And this is what it does. You throw it over the side from the ship, and it then spends 3 or 5 years in the ocean. And it mostly spends its time drifting at 1,000 metres, 1 kilometre depth. And then every month, or this says 9 days, depending how you program it, it does a duty cycle. It goes to work. It sinks to 2,000 metres, and once it gets there, it says, okay, I'm going to change my buoyancy. I'm going to measure things on the way up. It does that, gets to the surface, sends the data to the satellite, which then sends it to the nerds that want to get the data. And it does that for its lifetime, the battery. And it turns out that this is the snapshot of the population of these floats in the planet. It turns out in the Southern Ocean, we're getting more data from that technology every year than we did have in 100 years before that. So every year we're getting 100 times as much data as we used to get. So that's great. So I thought I'd tell you a few things about what I've done in my short career. It started out when I was a grad student, given the problem of trying to decide what happens when an oil well blows out at the bottom of the ocean. So you have this oil coming up. And when the oil well blows up, it comes with gas, natural gas, methane. And so it's buoyant, and traditionally you think that a buoyant plume rises to the surface. But I was able to show that, well, in the case of a bubble plume, the bubbles keep going to the surface, but the oil and seawater mixture can and does spread out horizontally, sometimes in multiple Christmas tree structures. And so while that work was done, 45 years ago or so, it saw its real application just 15 years ago when the Deep Horizon oil well blew out, and only half the oil, it turns out, actually reached the surface and did the damage to our birds and things. The rest spread out in the ocean interior and did damage to things growing on the shelves. Back to this, a schematic of the layered nature of the ocean. So you tend to think of the ocean as being some salty fluid out there that's perhaps well mixed. Well, it's not. Denser waters at the bottom and less dense at the top. And it's like this is a more nuanced view of the different density levels. And think of it like a party drink with different alcoholic, different densities. Now, a party drink, you can get a spoon, you can mix that up pretty quickly before you drink it, if you're brave enough. But it turns out in the ocean it's kind of hard to mix things that much. So this is an experiment done by people from Woods Hole Oceanographic Institution. They put out some dye just in a layer that was just 1 metre or 2 thick, and came back a year later and measured it, and it was spread out in the vertical by 30 or 40 metres plus or minus. So for a whole year, it's only spread in the vertical by 30 metres. And yet horizontally, it's moved and mixed by 1 million metres. That's 10 degrees of latitude. And so we have a fluid which is very layered. That party drink has got, it's very hard to mix those different colours up. And yet, this vertical mixing process is key to this vertical overturning of the ocean, which is the kind of thing that, when stopped, causes the film like the day after tomorrow. So it is a very important process, and a lot of us are working on mixing in various ways in the ocean. So it appears weak, but it has strong effects. All right, so what are these density surfaces? And so I've spent a lot of time in my career working on that. And one of the products that people use, given the world now, is neutral density. And if you have 3 different definitions of a surface starting from some point here, this is the old thing that we used to use for a century or so, and this is the new idea that we've given the world, and you can see they're quite different. So what is this thing? Well, if you think of yourself, the surface is up there, I'm taking you on an ocean journey, we're in the middle of the ocean, and we look around and see where's a spot from where I am to here, where's a spot that has the same density, so to speak. It means that that point there and this point here has a certain change in temperature and salinity, but they balance in terms of their effects on density. That's what we know to be the definition of such a direction, and this would be its mathematical definition. And when you do that carefully, you come up with these two new mixing processes called cabling and thermoboricity. So I coined the word thermoboricity only for President George W. Bush to start dropping thermobaric bombs on bin Laden many years later. So he liked the combination of the word temperature and pressure as well. So here's a density surface on which there's a change of temperature and a corresponding change of salinity. And mixing happens by putting plastic bag around these two parcels, bringing them together. Along the way, they fall off the surface because their compressibility is different, because its temperature is different. And when they mix intimately, then you get this other process, cabling. So I guess what I'm saying is when you're careful about what you mean by these things, sometimes brand new processes crop up. Moreover, and more harder to get your head around, is the idea, well, we've defined the surface. Think of it like a breakfast bowl, ceramic bowl. Everywhere on the bowl, you know what the angle is, what the surface is, what the tangent is. But if I give you a whole lot of tangents, it doesn't guarantee that it makes a surface. A surface gives you tangents, tangents doesn't give you a surface. And that's indeed what happens here. And so there's a way of getting fluid from the bottom of the ocean to the top just by going through these little spirals caused by this complicated nature of density in the ocean. And this is a picture of how much it can be. In some spots, it's red going up, some spots blue going down. And the units here are 10 to the minus 7 meters per second, which you might think is small, but that's 3 meters per year because there's pi by 10 to the 7 seconds in a year. And this is actually a leading order process in the Southern Ocean for vertical movement of water. All right, so what is heat in the ocean? Well, traditionally in the ocean and the atmosphere, we use something called potential temperature. Why? Because in situ temperature is a bit of a dead loss, really. You walk up, or you go in a car up a mountain by a kilometre, it's always 10 degrees colder. And even though the water parcels could be the same, you just move them up and down. So pressure itself, vertical excursions change temperature, but they don't change this quantity, potential temperature. And so for the longest time, a century or so, people have used this temperature in the ocean, but it has its weaknesses. And so this is a graph of the heat capacity, which it says, these figures here say how many joules of energy are required to heat up 1 kilogram of seawater by 1 degree Celsius. And the number varies by 5% depending what salt and what temperature you're at. And we've put up with that. And it turns out one day I was swimming before work and the idea came to me to try this other variable here, which it involves the same plastic bag around a fluid parcel moving to the sea surface, a reference pressure. But instead of asking what the temperature is there, you ask what enthalpy is there. Anyway, this theoretical work worked out much better than I had anticipated. I would have been happy with a factor of 2 improvement, but actually, fortunately, it got a factor of 100 improvement. And this now has become the world standard. I'll show in a minute. You can see that this is the difference between the old and the new variable. And for instance, if you're putting in warm water from the Amazon River into the ocean, then if you use temperature, you're wrong by 1.5 degrees Celsius worth of heat. So this issue now is put to bed. It's adopted by every nation on Earth through the Intergovernmental Oceanographic Commission of UNESCO. And we've redefined what seawater is, what humid air is, and also what ice is. So one last topic to talk about of my own work is to do with this vertical mixing in the ocean. How does this dense water here, how does it rise up? What allows it to rise up to the surface? So about 25 years ago, this observation was made as part of a larger experiment. The colours here are the mixing intensity. How much vertical mixing is there? How much stirring is going on? It's like some person's down there with a teaspoon stirring something up. It's actually, the mixing is mostly happening by the tide moving over seamounts. So there's a mountain range down there in the bottom of the ocean, just like there is on land. And the tide's moving over that mountain range and causing turbulence, which breaks in the fluid above. And it occurred to me, well, hang on, this mixing is increasing towards the bottom. What that means is that the actual fluid is moving downwards through the water column. It's moving down through density surfaces. So we want this to move up because we know there's bottom water forming somewhere. In the ocean basin at large, it's got to rise. And yet everything we measure says it's going down. So this is a conundrum. And so I proposed that what's really happening is, yes, in the ocean interior, when you're less than half a kilometre above the sea bottom, indeed, the fluid's coming down. But there must be a very thin region, perhaps 100 metres thick, in which there's an even stronger transport of fluid going up. And this was very controversial, and international conferences just didn't like this at all. But there's no other way. And in fact, now there's cruisers out there finding this stuff. That's very encouraging. And in fact, this transport up in these thin boundary layers is often 3 times the mean transport. So there's if we thought there was 1 unit of upwelling globally, there's 2 coming down and 3 going up. And this modelling study showed that. The last topic I want to talk about is conceptually very simple, but it fell to careful nerds like us to solve this. So a vertical plot of temperature often looks like this. The key thing being that it's curved like this. So in the bottom, this is 700 metres. The bottom part of the ocean, it's kind of, it's getting colder, but at a slower rate, and towards the surface, it's getting warmer faster. So it's curved. And in the olden days of, well, I guess I was born, but in the 60s and 70s, we used to go to sea and measure data every 20, 30 metres up here, but sometimes every 100 or 200 metres down here. And so you had a data point here, a data point here, a data point here, and the common thing was to just join them up with straight lines. So linear interpolation. Why did we do that? Because other things we tried, like cubic spines and things, didn't work. Didn't work because the data was so ununiformly distributed in the vertical. Anyway, we put our minds to that, got a better method, and it has actually a pretty large effect on the rate of warming of the planet, because these are two figures here. So this is the actual global increase of global heat content in the black as a function of time. I showed you a similar picture before with all coloured in blue underneath it. But if you use linear interpolation, you get the red curve. It turns out, so you overestimate the amount of heat in the ocean here in this period, and that means you underestimate the warming due to global warming. So it's happened because back in the day, in the 60s, data was sparse here, and today it's not sparse. We have plenty of resolution in the vertical. So this problem that comes about from linear interpolation only happens in the 60s and doesn't happen today, and that causes the bias. All right, so that's just an example where something as basic as a workable interpolation method doesn't blow up, can change the answers. All right, so I want to finish on this note. The take-home messages are two, really, and this is the first one, which is that if you force the planet with amount of carbon dioxide that was used during the ice ages, the ice age cycle, then you end up with effects that look like this. You know, a huge amount of ice in places you didn't expect. I mean, other places probably benefited. Maybe there was nice living conditions in the middle of Australia, I'm not sure. But that's, and I want you to walk away with a picture that a 5-degree change globally in the surface temperature is a big deal and changes whether, in fact, Canada has an economy or not, for instance, in this case. But now we're kicking the planet with something that may amount to the same amount of kick, and we're doing it in the other direction, of warming. And we know what this does. The warmer it is, the more evaporation. When we get rainfall, it evaporates faster. It's warmer, so the atmosphere holds more temperature, more water vapor. So when it rains, it buckets down. And we see this all the time, all over the place. The sea level is rising. It's accelerating. And it turns out the sea level will continue to rise for many centuries, even if we not only stopped our emissions today, but if we had some technology to stabilise our CO2 levels today at 425 parts per million, sea level will keep rising for several centuries. It's because of the memory in the ocean. The ocean's got a huge thermal mass, and it takes up to 1,000 years to mix all the ocean. So that's why the memory is there for the sea level rise. And this is our challenge. This is the figure by which humanity can gauge itself in the next century. This is our yardstick. Other things, wars come and go. This keeps on trucking. And it's a global problem. And it's a problem that has got every conceivable problem wrapped up in it. It's got the tragedy of the commons. We've got people saying, why should we do anything in Australia? We're only 3% of the world economy. Tragedy of the commons, first thing you learn in economics. So this is the message here, is that, first of all, the area under this curve is the temperature we reach. In other words, the total amount of fossil fuels that we burn over time, how many tons of coal and oil and gas we burn. That's the number that matters in terms of the temperature we reach. And the longer we delay serious action, if we want to reach a certain target of temperature, then the steeper our response has to be, the more extreme. Thank you very much.
Thank you very much. A really, not just interesting, but confrontational, I would have said, confronting a picture of where we're going for humanity. We've got plenty of time for questions. We have various people with microphones going around. So if you have a question, please start at the back there.
Yeah, hi. A very interesting lecture. My question is, there's a symbiotic relationship between the oceans and the atmosphere. What happens in the ocean is very much influenced, almost in the oceans is influenced by the jet streams, the stratosphere. And I say that because in the early 90s, I worked in a large organisation which was instrumental in implementing the HARP over-the-horizon radar, which has the capability of deflecting the ionosphere, punching holes in it, influencing weather, or just watching what's happening up and down the coast of China. Now, how can you How can we look at just the oceans or carbon dioxide without looking at what's in the atmosphere? And is there anyone doing similar research to what you're doing? And are we correlating those two research? Because if this is military, you can ionise the atmosphere over the Pacific with this HARP system. It's triangulation, 12 kilowatts of power into a point. Ionise the, my wording's wrong. Causes the atmosphere to ionise, and it takes out any rockets going from one side of the Pacific to the other. How do we get around that when we're looking at the big picture?
Okay, so, there's probably 1,000 oceanographers working on the climate problem around the world in various ways, and there's probably 5,000 atmospheric scientists doing the same thing. And the problems in the atmosphere are myriad, just like they are in the ocean. The atmosphere issues that we don't understand properly are clouds and aerosols, particularly clouds, and how they react. And the problem with the ocean has always been and still is, but could possibly be solved. One of the problems is the fact that our eddies, so in the atmosphere we have eddies, and they're called weather systems, right? And they're sort of half the size of Australia. In the ocean, exactly the same physics. It's a stratified fluid, denser at the bottom than the top, and it's a rotating planet. And the two things together cause eddies. Eddies is the instability. In the ocean, the eddies are a factor of 10 smaller, so a factor of 100 more per unit area. And that means our ability to model them has always been very, very weak. So a lot of, in fact, still today, most of the models that are used for climate prediction that end up in the IPCC documents every 5 years, these 3-volume sets, are done with coupled ocean-atmosphere ice models in which the ocean is not eddy resolving. It doesn't resolve these 100-kilometre eddies. It's parameterised. And so that's a step that we have to take, and we need bigger computers to do it. But yes, the atmosphere is a big part of the problem. It's just not where the heat resides, and it's not where the CO2 comes from.
Yeah, I mean, my view from what you were saying is most of the long-term issues with temperature and energy content are with the oceans and not in the atmosphere, just because of the density and the specific heat capacity. That's
right. 92% of the extra heat that planets receive from global warming is in the ocean. Yeah. But that doesn't mean that the atmosphere is, look at El Nino. It's a coupled instability. And there are other cycles like the Indian Ocean Dipole. There's 3 or 4 other cycles with common names that have got 10 and 20, 30-year cycles that are coupled instabilities.
Other questions in here?
Ivan Kennedy, University of Sydney. In your starting slides, you showed the very large increase in temperature in last year, but that was largely restricted to the Northern Hemisphere. One thing that did happen, an anomaly, was the Tonga volcano that put 10% more water into the atmosphere at the beginning of 2022. Do you think that could be a factor that contributed to that? After all, between a La Nina and an El Nino, there's 4% more water in the atmosphere during the El Nino, and generally speaking, it's about 1 degree warmer in the global atmosphere.
Yeah, you could be right. I'm not an expert on that, but yes, certainly these variations in heat content or surface temperature, I should say, are dependent on volcanoes, and mostly it's thought due to the aerosols that they put up, the sulfate aerosols. But water vapor is a big greenhouse gas, just like CO2, yeah.
I've got 2 questions. One is, in the Pacific Ocean, we are having sea sponge. Is it anything to do with the heat we are getting? That's one. Secondly, you have talked about current policy. After 2020, it is expected to decline. But I think we are not going by policies, we are going more by diplomacies. We try to find out some word to come out of the situation. Even in COP28, we have come out abated versus unabated things like that. So what is the true picture personally? I mean, not scientifically, personally, what do you feel? Where are we landing to?
I see us moving along the, well, I'm optimistic. I think the red curve is where we might end up, which is probably about 2.5 degrees worth of warming. But when I'm not, when I get out of bed the wrong side, I think something above the, maybe horizontal might be the right thing, in which case we haven't got a solution for another half a century. And it'll be warming by 4 degrees Celsius. So it depends, yeah, because it comes down to a political question, and how do we have all countries doing, and you can see how politicians in various countries you won't mention are very good at getting the population excited about weird things. And you can imagine if there's an international levy on some country because they haven't got the right policies in place. You imagine how that country would respond diplomatically, politically. So yes, it's an international problem with unknown ways of solving those diplomatic questions.
I think, Trevor, when I look at graphs like this, sometimes I have to also explain to people it is genuinely the area under the curve.
Yeah.
So even if we stop today, we still have inherited all the heating to date.
Yes, and because we've got, the concentration of CO2 is what it is today, it needs to come down. And how do we bring it down? Well, we bring it down by pumping CO2 out of the atmosphere and putting it somewhere. The only technology that has been talked about, and a small amount of money has been thrown at it by various governments and oil companies, is carbon sequestration. In other words, pumping liquid carbon dioxide into where fossil fuel, oil or gas used to be. Unproven technology, uncosted. I mean, it's expensive. It's much easier to stop emitting than it is to actually take stuff out of the atmosphere. So it's a problem without a solution. You can't pretend we have solutions to these things, but it's a problem that we know have to solve. And so all we can do is to start along the process of getting there, and hopefully there'll be some way of sucking CO2 out of the atmosphere, because there'll have to be.
A simple question. Is there any good news?
The good news is the breakfast was nice.
We have a question at the back there.
Thank you so much for your talk. It was very interesting. Full caveat, I'm not a climate scientist, but I was curious about whether in the coupled ocean atmospheric models, if you are looking at, forcing those with greenhouse gas emissions, are you accounting for emissions that, or CO2 that's released from the ocean floor from like deep sea trawling? Like, are there other, do we account for those emissions in those models?
I think the short answer is no, but if they were thought to be big enough, it would be easy enough to put it in.
I think there is an equivalent thing, though, on land in terms of soil carbon sequestration and the way we farm and things like that, and that certainly has an impact. Sorry, question here.
I'm also not a climate scientist, but interested in all of these topics. I've watched a film called 2040. I'm aware of Project Drawdown, and maybe a lot of people here are as well. They do somewhat offer suggestions of what might be helpful, but it sounds like from what you've said, we might not be able to mitigate, but simply stopping the fossil fuel impact might be the best thing that we can do. But on that positive side of things, what might be one or two of the top things that we could do?
So I think we have to do all of the above. So we can drive more efficient cars, we can drive electric cars, we can transition our economy or our electricity system to be totally renewable. And these things will have to happen, and they are happening. That's the good news, is that you can imagine in a decade or two there'll be no coal-fired power stations, for instance, in this country. But some things you need to put things in perspective. So in terms of trees soaking up, all the carbon, well, it's one of those things we should be doing. We should be, reforesting where we can. But it's not going to solve the problem, because even if you cover the whole of the planet, which is Earth, with trees, it'll soak up 30 years worth of our emissions. So yes, it's not insignificant. Even if we only cover 10% of the Earth with trees, it's soaking up 3 years worth of emissions. It's not nothing, but it's one of the things in an array, in an army of things we have to be doing.
So I'd like us to thank Trevor for a great talk, and that's my thing. I really enjoyed the book, actually.
Cheers.
So please join us again on Wednesday, the 1st of May, when Professor Jerry Swigers, who's the Chief Technical Officer of HySARTA Pty, will present a new approach to industrial production of green hydrogen, bubble-free capillary water electrolysis. HySARTA is a 2-time recipient of one of our most successful programs, the Physical Sciences Fund, and also one of Australia's most successful green energy companies. So please join us again on the 1st of May. Thank you.